On to today's live update here, straight from our random office IT tinkering. So yesterday, first time ever, we built the Linux kernel with Clang, they are of LLVM fame, low-level virtual machine. There, the compiler, of course, that Chris Lattner started, and then Apple employed him, and Apple used it for everything, and Google too and stuff, and then all the 3D vendors, AMD, Intel, and open source stuff for compiling 3D shaders and so on. So finally we could compile this. So far so good, although there is this really unfortunate regression that didn't allow me, because otherwise I would have this result already previous months or so. And with shared libraries that results in duplicate linked symbols, lookup, I don't know, some whatever. But today's video is about some other details. So yesterday this built forever, right? So on this Ryzen, not a paid advertisement, just what we have here, a few info. So this is the thing, AMD Ryzen 7 27 2708 core, and I used this to build everything here from yesterday and stuff. And compiling, I knew that compiling the Linux kernel on this VM node here took 10-11 minutes. That is an all modular kernel. If you say, yeah, but my kernel builds in 3 minutes, yeah, this is all modular, meaning you find modules, everything that can be a module is enabled as one, so that whatever you boot, whatever you plug in, whatever you have, this should boot and work with whatever esoteric HDMI capture card you plug in there. This is why this takes 10 to 11 minutes with, well, on a super fast machine, right? If you do this on a yesteryear's ULV Core i7 something, then in a slim and ultra compact something, then of course it takes an hour or so. But so compiling this yesterday with Clang took like forever. I obviously live streaming this and yeah, sitting here an hour, compiling it twice, totally not very comfortable. And it was clear to me that Clang felt extremely slower. And I posted here some updates. So welcome everyone in the audience, by the way. What audio is echo? Do I have? Sorry. Yeah, that comes from having. Was it 2-bit? Or is this was it 2-bit? I hope it was. Was it still? Damn, always technical difficulties. You name it. This is not a. But was it hearable in the beginning? Each time you. This is even the. I think it's the right microphone here. Damn it. Everything, something. So I benchmarked this. I spent an extra hour that I didn't live stream because it's probably usually too boring. So here are the results. So Linux kernel, I compiled. So usually my systems are size optimized because in the past it sometimes was even slightly faster and with less cache less cache utilization with smaller binaries and stuff. So that is what I usually built here the last decades, at least in 2005, like really long time ago, that was usually a good choice. So whole system, including the compiler, size optimized, and building a Linux kernel size optimized with GCC 5.3 that took 11 minutes. And then I benchmarked here yesterday's Clang 26 minutes. And so certainly that is more than twice as long and not amazing. And then obviously it's not fair to compile a 5 or 7 year old compiler from whatever base image we had in the deployment there. And I rebuilt locally GCC 9.2 to have a fair comparison. So GCC 9.2, to be fair, also got slower. So from 27% or so at least more than 25. I think it was 27 what I calculated. So just there you see a decade or so of code growth between 5.3 and 9.2, not 25% slower, just the build time, right? So I'm interested in testing stuff and waiting here and talking to you already. So that brings the difference to only about, well, still like twice as slow, right? And then I thought, yeah, well, somehow maybe something is not perfect, something slightly off or wrong. What does it, because GCC was back in the day C, in the meantime they also changed a little bit to very basic C++ and rewrote or gradually upgraded some code segments, some code areas of GCC. So they have not rewritten everything, but what they touch, sometimes they use some light form of C++ now. And given that, I spent the extra time, I rebuilt also only LLVM ceiling. So I rebuilt LLVM ceiling with O2, the regular speed optimization, what again I usually don't use on my systems. And that surprisingly or unsurprisingly brought the speed here, the compile performance quite down. And what I already was thinking, like, yeah, maybe this is a super advanced C++ code they're using, because they, in LLVM ceiling, they don't use the very most modern C++, but they certainly use much more modern STL templates for all kinds of generic algorithms and containers and everything. In ceiling, I would say it's fair to say a magnitude more than in GCC. So this, most of the part shows how much more sensitive modern template-based C++ code is for optimization. So this not really halved, but a huge chunk of 75% or so brought this down. Again, so this is then the time. So I rebuilt for half an hour. I rebuilt ceiling, LLVM ceiling, of course, both, because Clang makes, of course, huge use of LLVM for the low-level virtual machine compiler infrastructure there. And then rebuilt Linux kernel. So this took a couple of hours rebuilding all of this. And this is again still the same time for compiling the Linux kernel with size optimization. And yes, so you see that size optimization, unfortunately, maybe not the very greatest choice then for very modern C++ code. And some more notes. So that is that for you to know. Then maybe I also need to rethink my choice. Maybe I then rather want to size optimize everything. Also, here is some really crazy other numbers. So if you look at this ceiling, and so the binaries here become humongous or monstrous or enormous, whatever. And these numbers are huge. And then let's use H for human readable. So yeah, I'm not kidding. The compiler here, the C compiler, C language compiler front-end thing, 76 megabytes. That is, of course, not amusing. And the reason for this is most likely, I think I always saw that all the LLVM binaries and libraries become huge. Certainly amazing modern C++ and also support for all the targets. But this is a little bit very large, right? We can, by the way, check here with LLD here. So exactly what I expected. This is a result of, for me, what I disabled the other day here, LLVM. And also, I think I didn't commit this here. So exactly what I said the other day, that for me, I have this stupid regression that if you enable shared libraries, because otherwise you see the binaries become enormous. I'm also not understanding why people in modern times are becoming fans of static linking again. There's maybe Alpine Linux or Void Linux, something of that sort, of also 1000 Linux distributions. Some of them are now favoring static linking again. I really don't quite understand why. You have your setlib or OpenSSL linked into each binary, so you have a security or bug fix there. You need to rebuild everything. That is exactly what humankind, computer science stuff, society invented shared libraries for a couple of decades ago. Not really quite understanding that. And yeah, not only does this consume more disk space, but of course we have here a terabyte upgraded portable SSD. But of course this could also harm build time, right? Because it might be putting more pressure on the virtual memory subsystem, remapping maybe not as efficiently cache sharing shared libraries between all those processes running there, theoretically at least, maybe. And yeah, also for the code path, why is LLVM ceiling a little bit slower than even with like size speed optimization, still a couple of percent slower, right? That was Trying to that here. That is from 14 to 16, still a little bit slower. And this might also be because the binary size is larger and requiring the dynamic, it's still running the dynamic linker and still mapping and potentially even, yeah, certainly accessing with the CPU, even if it's not like loaded, which again, yeah, this is a 16 thread gigahertz CPU, but still also that even if it's mapped eventually also virtual memory into the process space, everything takes time eventually. So yeah, I really would, maybe I should redo this. Welcome to Canada. Maybe I should redo this with the previous stable version. Also, wait a second, I can't build Linux kernel with that. Nah, all the fun stuff. Yeah, maybe, but again, so much time gone. At least we have some data points, especially that I certainly want to use speed optimization then by default again, I guess. And somehow we really should fix this shared library bug because the binaries, again, they are, all the stuff is duplicated, right? So all this static library is linked into Clang and LLVM and all the other LLVM-AS assembler linker and all the fun stuff. And again, if I would rebuild Mesa now, the 3D stack, it would again factor this in and the Mesa stuff would become huge again. And yeah, anyway, I hope you found this interesting. If you're using Clang, make sure if you build this from source, make sure you build it with speed optimizations. If you have similar fancy modern template-based C++ codes, then yeah, also maybe size optimization not the very greatest choice. And this certainly also explains the other numbers of our pure Clang-based Musel system where compilation was so much slower because certainly we had everything size optimized. So maybe I want to rebuild my Musel Clang-based system with speed optimization. And here also benchmark and stuff, which of course I've done even with a Linux Magazine article in 2005 or whenever that was. And size optimization often was similar fast and sometimes in micro benchmarks even faster. And yeah, after a decade, maybe reevaluate this here live on YouTube because stuff changes, modern C++ code. And let's see, what else do we have? That's good. Everything was understandable. Canada, and people should get over themselves what do you mean with that. And yeah, I hope you learned something and found this data point interesting. For me, I still wonder, very theoretically, but the problem is now if I would special case this in T2, here our source-based Linux distribution, I could of course build the compiler with O2, but this would somehow contradict the optimization option if the user asks for size and then we build everything for size, but the compiler doesn't also make so much sense. Also, already you've seen the other day 4 hours or so integrating Ninja and Mason, and every time we special cases something, then more bugs and stuff. And even yesterday I found a bug with just switching to Clang causes a bug of GCC not wrapping the Clang compiler because the whole system wasn't built like this. So yeah, the more special casing, the more special bugs you get. One fun fact, by the way, I think unfortunately, is that you also learn something else if you are still here. I still need to decompress, download Linux kernel. Yesterday you saw all those probably that should do. Yesterday you saw all those alignment warnings of unimplemented options there in Clang scrolling by, and I took a look. Today I thought actually maybe this is due to size optimizations, but I was extremely surprised. Reading comments in the audience. I was extremely surprised to find that this is a global default in the Linux kernel, because I expected, because again, usually size optimized here, that due to we selecting the kconfig option, config cc opt size or whatever. Is it also decompressing here? Does it? Wait a second. Where is my? Oh. Hello. Maybe. Wait a second. What did I do now? Only live on. What have I killed now? Did this not do this here? Whatever. Anyway, so if you look into this is here in Arch x86, and I think it was just makefile alignment. So this is, as you see here somewhere, alignment, maybe here. Wherever it was hiding, align loops here. So here you have it, and so this is 6, if 32-bit, then that first chunk there, and then otherwise 64-bit, x86, AMD 64. This is not related to size optimization. So the first time I realized this, so it's not like our fault of choosing size optimization if the T2 user asked for this, but it's somehow hard-coded here in general for all. Also, by the way, fun fact, if this is calling, so call CC option, as far as I remember, this is a special construct here in the Linux kernel makefiles to evaluate if the compiler supports this option, and only includes this if the compiler supports this option. So actually, if Clang would actually simply not support this option, instead of outputting a warning, the Linux kernel make cable system would not even include this option that Clang doesn't support and warn about. But whatever. So yeah, there you have it. It's not size optimization. All kernels apparently, well, at least 64-bit x86, AMD 64 are always built with this. I really wonder why they have done this. I would naturally think this results in reduced performance, because then all the jumps and loops are aligned to 1 byte boundaries and not padded. I'm a little bit confused. I would think that not only the compiler should have the same default, I would personally naturally expect from my experience that should be slightly faster. Maybe I should, would be topic for another video, but benchmarking this would be a larger task, like running this for Ronix stuff there or whatever, because this is not something of just rebuilding the kernel. This is rebuilding the kernel, booting it, and running benchmarks. Would be interested if you want me to do this, but it is probably something for a whole afternoon, especially if you want to make this consistent and repeatedly and whatsoever. So yeah, a little bit unintuitive. Not the default 16 bytes. I'm really wondering, I sometimes would wish if they would make this special kind of configurations that they include a source line there. We do this because it's so much smaller, or benchmark really found it faster, but it's again a little bit unintuitive anyway. Maybe it has to do with the kernel code not running as much and they really want it more compact. But yeah, otherwise I only remember this, as I said yesterday, this was in previous times. I'm not sure if it's still here. Trans meta for sure. This kind of stuff would also be removed over the years. Transmeta. Yeah. There is actually makefile here. This is apparently, I think back in the day, but this is certainly removed. They had something similar for transmeta, because the code morphing obviously doesn't care and optimizes to very large instruction word anyway. And not 64-bit, no kidding. On the first glance, this looks like this was removed here. This is why I'm really surprised that they have done this for AMD64. Anyway, do we have any more comments? People take themselves, free content. Have you ever tried writing an EFI application? Not really, but maybe we will also do a proof of concept there with my kernel low-level stuff. I've only tinkered in Clover and Grub2, like this EFI magic stuff for this bloody MacBook there, with this secret EFI magic for not hiding the iGPU. Why are you asking? Tiano, I have this Tiano. I also hacked on Tiano Core for macOS booting and KVM, even for customers, got paid for that, amazing stuff. Yeah, it's a little bit, the EFI stuff is a little bit Windows style, it's a little bit, yeah. But once you get into the paradigm, it's not that bad, just load really, yeah, something of that sort, a little bit Windows kind of. Also all the GUID protocol stuff, it's, yeah, but you can get used to, especially if you tinker in grub2, then you have quite some runtime abstraction already, and for the most part are not getting too much in touch, at least when you are only touching grub2 core logic anyway, then it's more like a regular C program. But this is also something I really wanted to explore. I said this in the microkernel conceptual planning stuff, that it's a little bit funny that we have so much code duplication. You see the CLang binaries becoming so large, but also in grub, right? I called this out in the microkernel stuff, that in grub2, not only drivers, even for USB, serial port and Ethernet maybe, but all the other stuff like crypto stuff, LVM2 stuff, so, and even file systems, right? Native reading of XFS, non-XFS, BetterFS, and well, all of them, basically, maybe even ZFS, not sure. But this is what I meant with sharing the same modules between the microkernel and the bootloader. So basically, effectively having even using this kind of microkernel or exokernel kind of abstraction to use the same file system and networking modules and stuff, and basically skipping a bootloader. So having all the components and modules from such a microkernel be useful as a bootloader. And that would also mean having this EFI runtime glue. And of course, this is not unheard of, right? Because that is not only on the P3, but other IBM P series, PowerPC, and in general with kexec, all of those like P3, P series use kexec, the kernel execution of executing another Linux kernel directly. And probably, I guess, I'm not sure, but can Petit boot of kexec fame kexec FreeBSD? Maybe because the PlayStation had FreeBSD support, right? So no, but I never tried this, so I'm not sure if you boot FreeBSD or if you also boot this with Petit boot, no idea. But anyway, yeah, this is why soon, well, sometime between now and forever, but maybe this winter, autumn, rainy day, winter, some more file system stuff, some more bare metal, low level stuff, and trying at least some Hello World on Spark and MIPS, maybe the Octane or something, and or other embedded boards, just having some proof of concept stuff there, and then continuing with basic file system. Obviously, if we start from scratch, like C++, a little bit more readable with a few templates. That stuff is like endianess stuff and so on. And bit packing stuff is a little bit more readable than open-coded C. Maybe, certainly, we start with something as simple as FAT before we start into reading ext2 or other super complicated BetterFS stuff. Yeah, some comments in the audience, and then that's it for this live stream. By the way, fun fact, as I promised, I put this build kernel in operation on a data center VM that I'm running this Musel CLang system, and so far it still works, so I've not yet had any issue with this CLang build kernel from yesterday. And let's see, without Unicore, then CLang, as long as you have the header for the EFI system tab, you don't even need any extra libs or headers. Did you write in C++? I did it in Rust, wasn't too bad. Okay, that is interesting to do this in Rust. What do you work on something Redux OS related, or the Intel has a Rust hypervisor actually. No need to recompile, cross-compile either, at least. You get FS file system. I didn't see, just on shell and stain EFI mode. That's cool. Amazing stuff. Thanks for the comments. I hope you learned something, or this kind of data points are useful here in terms of such build times. And yeah, just as myself, when you complain this stuff is totally slow, then maybe reevaluate if your own compilation and optimization are a result of that. That's it for this video. Maybe another later again. Probably better to keep them short. Hope to see you soon for all the next stuff to come.